All right, so we're here with Dr. Kevin Trenberth at NCAR, and I think I want to start off very basically and just talk about what are greenhouse gases and what do they do? What purpose do they serve?
Well, the main one that we talk about is carbon dioxide, and any gas that has more than two atoms to the molecule, so CO2 is carbon dioxide, H2O, water vapor, and methane, CH4. All of those are greenhouse gases, and they interfere with the outgoing radiation that would normally escape to space. And they provide a blanket for the planet. So they're heat-trapping gases in that regard. And many of these are increasing because of human activity. So carbon dioxide has gone up by over 40% since the pre-industrial times, but more than half of that has occurred since 1980. And so the rate of carbon dioxide increase has been quite outstanding, and it's directly related in this case to the burning of fossil fuels.
Okay, so some will say that, okay, it's a trace gas, it's less than 1% of the atmosphere. What would the Earth be like today if we didn't have the pre-industrial revolution levels of carbon dioxide present?
So without the greenhouse gases, without the carbon dioxide and the other greenhouse gases, the planet very likely would be uninhabitable. It would be 35 degrees Fahrenheit cooler, something like that. Okay. So we can do experiments of that nature, but the continents would be perhaps covered with ice, and then ice itself is reflective, and so who knows exactly what the planet would look like under those circumstances. But we need these greenhouse gases in order to have a habitable planet, and then water vapor, which is relatively short-lived, is a feedback. So once things warm up a little bit, the atmosphere can hold more water vapor, which is also a greenhouse gas, and things warm up a little more, and that turns out to be a very important part of the process as well.
Okay. Now, water vapor, as you mentioned, is a greenhouse gas, and it exists, many times in greater concentrations than carbon dioxide. So I've heard the argument made, well, why are we so concerned about carbon dioxide and not water vapor?
The issue with carbon dioxide is that it's a long-lived greenhouse gas. It has, on average, a lifetime of more than a century, and some of the carbon dioxide actually hangs around for more than 1,000 years before it gets taken up by the system in some way. I mean, the way in which it's really removed is through the oxidation of rocks and so on, the weathering of rocks, and it goes into the ocean, and it gets taken up by organisms within the ocean, and the shells and the bones fall to the ocean floor and sort of get taken out of the system and form limestone. There is a lot of carbon dioxide taken up by trees, but then the trees decay, or the leaves decay on the forest floor, and that carbon dioxide goes back into the atmosphere, so that part is sort of recycled through the system. It's not really taken out of the system. In contrast, water vapor has an average lifetime of about 9 days. And so, and the water vapor is concentrated in the lower part of the atmosphere. It's not well mixed through the entire atmosphere. This is one of the other ways we know that carbon dioxide has a long lifetime. It's emitted from industrial regions, and especially in the northern hemisphere, but the concentrations are going up globally at the South Pole, for instance, and it's therefore not only well distributed globally, but it's also well distributed in the vertical, and so it has an influence throughout the entire atmosphere, whereas water vapor tends to be very local, and it very much often tied to the oceans.
Okay. Alrighty, so we have estimates of carbon dioxide farther back than the readings at Mauna Loa, or at least estimates of that. And that record, at least I have seen some people talk about this, that the temperature increase actually led the CO2 increase. And so the counter argument is, if CO2 didn't lead temperature then, why do we think it's leading temperature now?
If you look at that record, so you're referring, I think, especially to the ice core record in Antarctica. And so Greenland and Antarctica, we have quite good records. So we can go back about 800,000 years fairly reliably now with the carbon dioxide record, with the methane record, with the indications of the temperature record on a sort of a global basis at least, using isotopes. And the best analysis suggests that the changes in temperature may occur 100 to 300 years ahead of the changes in carbon dioxide. And so in this case, the temperature goes up a little bit, and there are two main sources of carbon dioxide and methane under those circumstances. One of them comes from the oceans, and so the oceans warm up a little bit, and there's some outgassing from the oceans. This is similar to the sort of thing that if you have a pot and put it on the stove and turn the heat on, there are bubbles that come out of the water. And so this is gas that's been in the water that comes back out, and the solubility is less as the temperature warms up. So outgassing is an important process in this particular case. The second major source is on land, and this relates to the sort of thing that goes on in a compost bin, that if you have vegetative matter and there are certain kinds of bacteria that cause it to decay, if it's dry, then it decays with a certain kind of bacteria relatively fast and produces carbon dioxide. If it gets wet, then it decays at a somewhat slower rate, but it produces methane. Okay. And so as the soils warm up, all of the vegetation matter that's in the soils starts to come back out, either in the form of methane or carbon dioxide, into the atmosphere. And so soil carbon is another source of carbon dioxide under those circumstances. Okay. So the thought then is that the increase in carbon dioxide and methane, which are greenhouse gases, is a feedback process. So the original change, which we think is actually caused by the change in the orbit of the Earth around the Sun, and sometimes maybe a little bit by the Sun itself, then that increase in carbon dioxide then amplifies the original temperature changes, and so this is the sort of thing which leads us into and out of the major ice ages that we've seen over geological times. So in that case, we think of the carbon dioxide primarily as an amplifier and a feedback process, but fundamentally it's a greenhouse gas that has a long lifetime, and so now we're increasing carbon dioxide and nitrous oxide, methane from human activities. These are actually playing a role of causing the temperature to increase and the cause of climate change.
So this is really the first time that we have forced carbon dioxide to increase as opposed to it increasing as a response to something else.
Yes, this seems to be the case. I mean, maybe humans have done a little bit of this for some time simply by lighting fires once we discovered fire. But you know, the thing is we've started burning fossil fuels, digging it out of the ground, and the rate of increase of the burning of fossil fuels has really skyrocketed since about the 1950s, and we had major problems as a consequence in the 1970s, and that is when many of the Clean Air Acts came in many countries. China is still catching up on that process.
Exactly. Okay. So tomorrow, Richard and I are heading to Barrow.
Yes.
Which is going to be interesting. And the one thing that struck me about that is that the majority of the warming has occurred in the Arctic, if I'm not mistaken, and that even the earliest climate models suggested back in the 80s that that would be the case. I've always wanted to get a clearer explanation and understanding in my own mind as to why the Arctic would be expected to warm quicker than the lower latitudes.
The high latitudes, of course, is the region where snow and ice play a key role. And so there's a process called ice albedo feedback. And this relates to the idea that if there's snow and ice around and we warm things up a little bit, that melts, and then instead of having a bright white surface which reflects the sun, instead the darker surface absorbs more solar radiation, and therefore it gets even warmer still. And so this is the amplification effect. And this is primarily what those early climate models were talking about. Now, some of the warming that has gone on in the Arctic has been very much relating to the atmospheric dynamics. The the ridiculously resilient ridge along the west coast that has led to the drought in California has brought some very warm air up into Alaska, such that the Iditarod had to be firstly postponed, and there was not enough snow and delayed, and it was moved to an area north of Fairbanks, as it turned out. And that warm air has gone right up into the Arctic, and so the Arctic sea ice at the moment is at an all-time low for this time of year. But of course, that cold air didn't just disappear. That cold air actually came down across the eastern part of the United States. And so the dynamics also can play a role in this. And but once the Arctic has warmed, this feedback process is the thing that comes into play and cuts down on the sea ice in particular, and then the darker ocean takes up more heat, and that has a long lifetime.
Okay, that makes perfect sense. Climate models. What do they do well? What don't they do well? And I guess as a corollary to that, how do they handle feedbacks? Or is there a chance they're missing a feedback that could save us from continued warming?
Well, the climate models consist of the entire climate system. They consist of, in the atmosphere, atmospheric models, which are used and exercised every day for numerical weather prediction, for the weather forecasts that we see every night on television. And, you know, these have gotten better and better. And now we know that they can't predict the weather more than about 2 weeks in advance, because small changes actually get amplified through a process which we refer to mathematically as chaotic growth of these weather. Small perturbations grow. But the atmosphere is in these cases getting very good. The difficulty with the climate system is we have to attach an ocean to it, a land surface that's fully interactive, all of the glaciers and ice masses and so on. And so the computational burden goes up enormously. And then we also need to run for much longer periods of time. And so we can't run the climate models at the kind of resolution, the high resolution that we run the weather models at. And so we know we're shortchanging ourselves when we do that kind of thing. The models do the overall dynamics of the atmosphere, all of the winds and the weather, reasonably well if we can have adequate resolution. But some of the climate models maybe don't do clouds as realistically as we would like. So the models don't necessarily do the clouds as well as we would like, and this actually becomes very important for the longer term climate system, because clouds are very bright and they interfere with the sun and the flow of energy through the climate system in that regard. The ocean is also quite complicated. We have the phenomenon known as El Nino that causes large fluctuations in the weather and climate system from year to year. And the models do have El Nino events in them, but they're not quite as realistic as we would like them to be in order to have full confidence that they're doing quite the right thing in the climate system. El Nino can be regarded perhaps as a relief valve in the Pacific. It takes up heat and then moves it around and then gets it back into the atmosphere and ejects it from the system and regulates the temperatures in the tropical Pacific as a result. And so we have to be able to do all of those kind of processes with fidelity, and we do a pretty good job. The models are certainly getting a lot better, but they're not perfect by any means. They're tools in this regard. So they're the best indicator we have as to what we expect to happen when we run these models, but we do need to be aware of the fact that they're not perfect.
Okay. Now, that's a perfect segue to the next question, is that one thing that the skeptical community, if you will, harps on is that the warming stopped in 1998. We've had a 17-year hiatus, and none of the climate models indicated that would happen. Is there a chance that the IPCC maybe misrepresented the climate model's ability to portray this as a linear increase in temperature when people like you know that it is not going to be that way, that there are going to be ebbs and flows? But number one, I mean, I guess, is this hiatus real? Is it an indication that that the science is all wrong, or what do we make of that?
You know, global warming means that the carbon dioxide is increasing relentlessly upwards. But the global mean temperature certainly fluctuates from year to year because of things like El Nino events and the weather and so on. And so there are these natural fluctuations which interfere with that relentless increase. And so global warming doesn't mean that the temperature increases relentlessly one year after the next. And in fact, one way of looking at the temperature record is that rather than a gradual increase in temperature, maybe it in some ways is more like a staircase. It actually goes up, and there's certainly a way of analyzing the temperature record that shows it a little more like that. Mm-hmm. Now, you mentioned the year 1998. Well, 1998 was a very special year. 1997-98 was the great big El Nino. And that's when the term El Nino actually went from a scientific term to become part of the vernacular. And in that particular event, a tremendous amount of heat came out of the ocean into the atmosphere, produced disruption in many weather systems, but it produced a mini global warming. And that meant 1998 was the warmest year in the 20th century by far. If you look at the record since 1970, which is when global warming sort of really kicked in to be large enough to exceed the natural variability, then the main time that actually stands out is not so much the last decade or so, it's actually 1998 more than anything. Mm-hmm. But certainly there has been a little more of a plateau. It hasn't warmed as much in the 2000s as it has in the previous few decades. Should we say. Mm-hmm. And we want to understand that kind of thing, and there's been quite a number of papers, including some of my own work, that's been published on that now. And it relates very much to a phenomenon in the Pacific called the Pacific Decadal Oscillation, which relates a little bit to more La Nina events instead of El Nino events. And so the stronger trade winds in the Pacific has piled the warm water up in the Western Pacific, and it actually hasn't warmed in the Eastern Pacific. And this has changed the weather patterns throughout the tropics and, in fact, throughout the globe. This has now relaxed. And so it began to relax in early 2013, and now we have a relatively weak El Nino event going on, but 2014 is the warmest year on record. Mm-hmm. And there are some pretty good indicators that suggest that maybe this hiatus is over, and we're about to go into one of these stages. 2015 could well become the warmest year on record, warmer than 2014, the way we're going at the moment. And so maybe we're at the next one of those stairs and going up to sort of the next level. The trouble is, once we go up through one of those stairs, we oscillate around a different level, but we never really quite get back down to the previous level. And I think that's one way of interpreting what this sort of decadal variability does to the overall increases in temperature that we see.
So it's not a sine wave, it's a stair step.
It's a stair step.
There have actually been some that have asserted that that NOAA or whoever has actually doctored the data in order to make it look like there is more warming than there's actually been. I mean, that would obviously be very troubling for anybody who appreciates the integrity of science, but how did that even get started? I mean, how could that assertion have possibly been made?
There are changes to the temperature record that are made all the time. Unfortunately, the temperatures are not made mostly for climate purposes. They're made for weather purposes, and so stations move. The place where you're making the measurement, cities build up around them and have influences. The station moves to the airport. An airport gets bigger and all these jets come in and stuff like that. And so there are these other kinds of influences that you need to understand, the effect of urbanization and land use change and so on. But there are a lot of rural stations all around that are largely unaffected by these kind of things. But even those, a farmer might be operating one, and they move them as well. And so you have to take these things into account. So the temperature records are continually being adjusted, both up and down, When one station gets moved, it's checked very carefully against all the surrounding ones to see what the effect of that move is. An obvious thing is if you move it to a higher level, then the air tends to be a bit cooler at higher elevation, and so the fluctuations go on much as before, but at a slightly lower level than they were before, and you need to take that into account.
Okay.
So this is the main motivation for the changes that are unfortunately necessary in the record. And they're done very carefully, and there are changes both up and down. There are some temperature sites that are very poorly sited. The standard measurement is over a grass surface in a particularly vented box that is about 4 feet above the ground. But sometimes these things are put on the top of a roof or something like that, and they might be in the blazing sun and have very poor sightings. And it's easy to document some of these and say these are not representative, and we're well aware of that kind of thing. But this is one of the difficulties. Now, of course, the temperature record is only one indicator. And so there are other kind of things like the global sea level rise and the melting of ice and other indicators that reinforce the idea that the planet is warming. It's not that we're confined to looking at temperatures. And over the ocean we have sea temperatures. There's actual measurements of the ocean water itself in various different ways that are also corroborating the nature of the changes that are going on.
And you know, one thing I didn't realize until the short course that I saw you at a couple years ago was the acidification of the ocean, that I often thought that all of this occurred above ground and above water, and found out that's not really the case.
Well, the heat penetrates into the ocean, and the carbon dioxide also penetrates into the ocean, and indeed does cause acidification of the ocean, and this has effects, and then in some places this can actually be seen on small marine organisms. Their ability to form shells is one of the threats in that regard, and relatively small changes can make a big difference to some organisms.
The sun, there's still some that claim that there's the sun is what's driving all this. And I have read and heard in the past that the smoking gun against that argument is that the troposphere has been warming and the stratosphere has been cooling, and if the sun was driving it, both of those would have been warming up. Am I stating that accurately?
That's correct. That's certainly part of the understanding of what the changes in the sun would do. But we have good measurements of what's happened on the sun since 1979, which is when satellites were launched above the atmosphere and they can actually measure the incoming radiation from the sun. And so we see the sunspot cycle, and the amplitude of that fluctuation is of order 1/10%. It's really quite small. And then in recent times, we had solar minimum, which may be, if anything, a little bit lower than the previously measured solar minima. This is the period from about 2003 through 2009. And if anything, the sun is actually going in the wrong direction to produce global warming. It may have contributed a little tiny bit to this so-called hiatus in that period, but since then the sun has gone into an active phase again. And just last week there was a record-breaking solar flare that caused quite a lot of concern on places like the space station. And so there are natural fluctuations in the sun that occur. The ones that we've measured are not large enough to really cause climate change. They would be if they were sustained for centuries at a 0.1% level. And so changes in the sun are certainly potentially very important. But so far our understanding is that they're small enough that they really have not caused major climate changes in the last 50 years or so.
Okay, all righty. Let's see. Are you at all frustrated at times that even people or organizations that believe the science, think that there's an issue that needs to be dealt with, can sometimes go a little bit above and beyond common sense and overstate certain things, and then that takes away credibility from the good science? Is that something that you have noticed or deal with?
Yes, and so there are two sides of this kind of thing. There are people who are apt to overemphasize some of these things, or focus on very particular aspects and leave out some of the other sides. And then there are some who may be driven by various kinds of ideological agendas of different kinds that are actually carrying out disinformation campaigns. And the thing is, there's enough natural variability in the climate system, and we have weather events which cause heat waves and also cold spells, and so you can choose on the heat wave and say, oh, look, it's global warming, and then the cold spell, well, what about that? Oh, there's no global warming. You could even take a snowball into the Senate and say, look, there's no global warming, or something like that. And neither of those extreme views are helpful. There's a tremendous amount that we do understand. There's a tremendous amount of evidence to support the fact that the planet is actually warming, and from multiple lines of evidence. And the real debate ought to be, what do we do about this, rather than really questioning the underlying science. And so as scientists, we have a duty to try to understand as best we can what is going on and what the causes are and what the implications are for the future. But the decisions about what to do about that is something that the general public, the politicians, everybody needs to be engaged in helping to decide. And so there are many factors that come into play there, which relate to value systems and how much you value the future generations and the kind of planet we're leaving them, and all of those kind of things.
Now, one of your colleagues, Kerry Emanuel, has described in his mind this issue as being risk assessment, that even if there is a relatively small chance of something horrific happening, and you had it within your means to reduce or eliminate that risk, why wouldn't you do it? Yes. Is that a reasonable way to approach this issue? Not necessarily that we're all going to be in flames in 50 years, but that, like car insurance, that analogy has been used, where maybe we could roll the dice and never buy car insurance and get away with it, but we do it off the off chance that something bad could happen.
Yeah, firstly, this is a global problem. Carbon dioxide has a long lifetime. It spreads globally, so what we do affects everyone else on the planet, and what the Chinese do affect everyone else on the planet. They affect us as well. The Chinese are changing our climate. Shouldn't we be concerned about that? Mm-hmm. We're changing their climate. Shouldn't they be concerned about that? I don't understand why people aren't more upset by that kind of thing. We are making the best projections we can right now, right, with the tools that we have, as to what will happen in the future. And the real worry is that sometime out about 50 years from now, the changes could be large enough that many of the things that we do today will no longer be viable. Much of the agriculture that we do right now may no longer be viable where it is right now. Forests that currently grow and ecosystems that grow in certain regions may no longer be viable there. In other words, if there's a wildfire, that forest won't grow back. It doesn't mean some other forest, a different variety of trees may not come back in that particular location. But the changes at that point could be large enough to be seriously disruptive. Mm-hmm. And that should be a major concern for society. And we should therefore take steps, I believe, in order to reduce that risk if we possibly can, and slow the process down. As we can understand it better and see what is happening, we can adapt to it and plan for the changes much better than if they are really coming at us at a really fast pace. And right now, the nature of the changes that are occurring are probably something like 100 times faster than they occur in nature. So it's not that we've not had climate change in the past. We certainly have, but it occurs at a slow rate, and everyone can adjust to it as it goes along. That is probably no longer the case.
Okay. A difficult question to ask, but could you be wrong about all of this? I mean, despite all of your colleagues' best efforts to understand this from a science standpoint, is there a chance that things will turn out differently than we currently think?
There's some chance. I mean, we try and put what we call error bars, or a range of possibilities on things with regard to the temperatures. I mean, the things we understand the best are what we call the thermodynamics, the things that are related to temperature, which also affects the amount of water vapor that the atmosphere can hold, and so that affects storms. But the parts that we don't understand as well are the detailed dynamics, all of the inner workings of the weather systems. And so one prospect is that as the climate changes, the weather systems become more vigorous, there's a bit more cloud generated. And if there's more cloud generated, maybe that can block the sun and slow things down a little bit. Okay. But it can't actually make it go in the other direction. It can certainly be one of the factors that makes the climate change a little bit less than it otherwise would be. But we're talking about, taking something which is really extreme down to something which is still a problem. And so with global warming, it's one way of thinking of it. It's not so much that the temperature is going up by a certain amount at a particular time. It's going up by that amount, but maybe it could be plus or minus 20 years. It's going to happen sooner or later. And the main thing we want it to do is, if at all possible, is to make it happen later. Slow the process down, if at all possible. And so there are some of these important details that we need to understand better indeed.
And I guess the last thing that I'll ask is, why do you, and you've already addressed this to some degree, but why do you think there is such a vitriolic divide on this and other issues? I mean, this isn't the only one we see this in, but and what can we do? What can science do to help alleviate that? Words are escaping me, but the animosity between these two sides, two philosophical sides.
So certainly my approach to this is to say, well, let's deal with the parts that we're dealing with science, all of the evidence and the physical understanding, the facts that we're dealing with. And there's a tremendous amount of those relating to climate change that certainly suggests that it's a real problem, and it could become extremely disruptive as we move into the future. And the issue then is, what do we do about it? That's really what the question is. And there are many people in vested interests in the coal industry, the fossil fuel industry in particular, and there have been many campaigns that have been financed by the fossil fuel industry and others, the Koch brothers and others, to carry out misinformation campaigns, to cast doubt about the science, to amplify the doubt. Merchants of doubt is one of the terms that's often used for this kind of thing. And these kind of people have been around for a long time with regard to things like tobacco or acid rain or many other issues, maybe healthcare issues. And so some of this relates very much to ideology and value systems. It relates to the potential role of government. Since we're dealing with a global problem here, this is really relating to the fact that the atmosphere is a global commons, and we treat it as a dumping ground and put our own pollution into it, but it becomes part of a global problem, and therefore it really can't be solved properly by an individual, by a city, by even a country. It needs to have international involvement, and so there are important international negotiations going on, which will culminate in Paris later this year, to try to get everyone on board with regard to this. But it becomes very difficult because of the different viewpoints, and there are some people who think that we can take short-term advantage and exploit the atmosphere, use it as a dumping ground. And there's been statements maybe it's not profitable to control greenhouse gases, and extreme points of view like that. And yet it has consequences for everyone, and especially many innocents who are suffering from higher sea levels and stronger hurricanes and things like that. So it becomes an ethical issue, and value systems come into play. I think if we were to recognize that and talk about it and frame it in that way, we might make a little more progress than these disinformation, and at least let's try and settle on the basic facts that we're then trying to build decisions about.
Do you think we can change our world and do it in such a way that it doesn't destroy our economy?
I certainly think it's possible, but we're not there at the moment, and there need to be some substantial changes. I mean, at the moment, I think that there are many subsidies for fossil fuels in various ways, and yet fossil fuels, when you burn them, put carbon dioxide in the atmosphere, they put pollution in the atmosphere, they cause diseases like asthma. And so there are costs, but the costs are borne by somebody else, not the person who burned the fossil fuels. So the way I think of it is, shouldn't there be a user pays element to this? That if you burn something, you pay some of that downstream effect. And if we could have a price on carbon, and this is referred to sometimes as a fee or a carbon tax, or there are other ways of implementing some sort of a cost on that, then you would see the whole economics change, and the private sector would respond, I think, in a tremendous way, and you would see a tremendous amount of innovation. And so this relates especially to renewable energy, and renewable energy is already advancing at much greater rates than they thought it would 10 years ago with wind power and solar power and so on. But it needs to continue, and yet the playing field is not level between renewables and the fossil fuel industry at the current time. And so this relates also to the U.S. administration and what the EPA is trying to do with the Clean Air Act and the programs that are being developed, which I think are actually very innovative, but they have to be implemented at the state level. And so there's all of the state politics comes into play as well.